Okay, so similar to the difficulties that we needed to get past when we defined addition, we are going to run into some issues when we try to define multiplication. So they're not issues we can't get past, but um, I just want to show you why it's inherently a little bit more difficult to write down the definition of multiplication. So suppose that we have some polynomials in z adjoint x. Let's just come up with some random simple examples that won't take too long to multiply. So that's our p, and maybe our q is like -3 plus 5x cubed, something like that. So p times q is not anything new. Okay, this is just take p and multiply it with q. You all know how to multiply polynomials. You just FOIL, or you distribute. It's like advanced foiling, right? So we multiply our 1 in, we're going to get -3 plus 5x cubed. We multiply our x in, we get -3x plus 5x to the fourth. We multiply our 3x squared in, we're going to get -9, oops, plus, it should be plus -3, sorry. We're going to get -9x squared plus 15x to the fifth. And then after you multiply them, you sort of combine like terms. And we lucked out with this. So there's no combining that actually happens. But in particular, what we would do here is we have to sort of take all the possible products, right? That's what we did, take all possible products. And then combine terms of the same degree. Now it turns out I accidentally picked a situation where there aren't going to be any terms of the same degree. That's okay. But that's what you would do. So when we write down the definition of multiplication, it's going to have to take all possible products, and then it's going to have to also simultaneously have a way of combining terms of the same degree within the definition. So the definition is inherently going to be complicated. And let me point out one thing, sorry. The degree of the product is 2 plus 3, right? Because what's the highest degree we're going to get from this product? Well, x squared times x cubed. Now that's not always going to be true, but it is true when our coefficients are in z. So let's write down a definition for multiplication. So definition. So given two polynomials, p and q in z adjoint x, what we're going to do is we're going to write, as in the case of addition, p as some random polynomial and q as some separate other random polynomial, possibly with a different degree. So it'll go up to bm x to the m. Here an and bm are both not 0. It's just what it means to say that we have two polynomials with integer coefficients, and so the coefficients are in z. Then p times q is the following polynomial. It's the polynomial c0 plus c1x plus c1x to the L, where L is going to be the sum of m and n, and the coefficients that show up have to somehow capture all possible pairwise products and combining the like terms. So how could we get a constant term, a C0, for example? Well, you would have to multiply the two constant terms. So C0 is the only possible pairwise product that would produce a constant, something without an x on it is that. Now, how could you get a linear term, a term that just had, or a degree 1 term? Well, you could get an A0B1 or a B0A1. So C1 should be the product of A0B1 with, A1B0. Let's write our A's first. What should C2 be? That should be all ways of getting a quadratic. So you're going to get let me use a different color. You're going to get like A0, B2, B0, A2, and you're going to get A1, B1. So you're going to get A0, B2, A1, B1, A2, B0. Another way of writing that same thing. And so on. You get all pairwise products such that the indices sum to the degree. So notice here, 0 plus 1 is 1. 1 plus 0 is 1. Notice here, 0 plus 2 is 2. 1 plus 1 is 2. 2 plus 0 is 2, and so on. So what we're going to get is CI, the general term, is going to be the sum A0BI plus A1BI minus 1. And you keep going until you get to AI minus 1B1 plus AIB0. It's the same pattern, but it's just a general I now. And in particular, when you stop, you're going to stop at Cm plus n, because that's our CL. It's an L up there. L is m plus n. And that's going to be A0Bm plus n plus A1Bm plus n minus 1, and so on. Am plus n minus 1, B1, Am plus n, B0. So that's what the coefficients are. And now, if you sit here and you think about this for a second, that doesn't make any sense to write down, because Bm plus n is more b's after the degree. The degree is Bm, so as long as n is at least 1, Bm plus 1 is not there, right? There's no Bm plus 1 here. There's no An plus 1 here. So what is going on here? Well, we have to do that same extension by zero trick. So instead of saying it, what we're going to say, instead of saying it like we did in the addition video, what we're going to say is where it is understood. So, or if you like, where it is defined, or however you want to write it, where it is understood that bk is 0 for k bigger than m, and aj is 0 for j bigger than n. Okay, those guys are just 0. And if you sit here and you think about Cm plus n for a second, let's do some index arithmetic now that we've defined the multiplication. If we think about what Cm plus n is, this is very helpful. It's made up of terms that look like ai bj, where what? I plus j has to sum to m plus n, and that's it, right? So let's think about this. What happens if I is bigger than n? Well, if I is bigger than n, then ai bj, I messed up the indices here. We're at an index that's bigger than n, so that's 0. Great. What happens when I is less than n? Well, then j, which is m plus n minus I is less than n. So this is saying that n minus I is positive. If we solve that, we get j is m plus n minus I. This is a positive term here. That's bigger than 0. So if we have m and we add something positive, we're bigger than m. So if I is less than n, then j exceeds m. But when j exceeds m, the coefficients for b are 0. So in this case, ai bj is 0. So what are the terms that contribute to Cm plus n? Well, if I is bigger than n, it's a 0. If I is less than n, it's a 0. If I equals n, then I plus j equals m plus n. This is the same as n. This tells us that j is equal to m. So if I equals n, then j is equal to m, and we get the term an bm. And it turns out that the leading term of the product is just the product of the leading terms of the polynomials. This is completely unsurprising. Although the index arithmetic might be somewhat new to you, the result is not surprising. So all this is saying is the leading coefficient, if we go up, of the product is actually just an bm. So we could, if we want, think about that as being what the leading coefficient is. And of course, what else could it be? How could you get a term with degree n plus m? Well, you have to multiply the top two. And then the lowest coefficient is the product of the constant coefficients. But all these these guys in the middle, they involve some mixed terms. And the mixed terms, the way in which we write those down is with this complicated formula. All right, great. So we've introduced the definition of multiplication. It's kind of terrible, but it's inherent. We all know why it has to be like that. It's because it's trying to capture two things. It's trying to capture taking all possible products, then combining like terms. So the definition is long. All right, so here's the end of the definition. And then we observe, though, that the leading term is what it should be. It should just be the product of the leading terms. So the definition kind of makes sense for what we know for what happens with polynomial multiplication.